conceptually, this is one of the more bizarre quantities in physics that we deal with. It's one that you're familiar with already, you should be familiar with already, for a whole bunch of different reasons, just in that it exists. You guys talk about voltage. We talk about voltage somewhat regularly. We talk about as far as like the voltage at the outlet at the wall, and we talk about the voltage of. Well, you guys should have done circuits last year. You talk about the voltage drop over certain elements in a circuit. But now we're going to start applying these ideas of voltage to single charged objects. We're going to remove the concept from the circuits, and we're going to talk about what it means. Voltage is weird. And this is I think this is the first time in this course that I will say this to you. When voltage makes you uncomfortable, it's not if, it's when. It's one of those things where you just have to accept that it is the way it is, even if you don't like it, and use it. Yeah, I will. Yeah, several times throughout the next couple lessons. Where it's one of those things that, well, with what Ashton was talking about earlier, you finish a course and you're like, I have no idea what just happened to me. And you go on to the next course and then you use the old stuff and you're like, oh, now all of a sudden the old stuff makes sense and it's the new stuff. I have no idea what's going on. Voltage is likely going to be one of those things where you're just like, you get to the end of it and you're like, I did some stuff. It worked because I got it right, but I don't really have a grasp of what this thing's getting at. And for some of you, that might not be the issue. But do be prepared for the fact that voltage is weird in the ways that we're going to deal with it. And sometimes we just got to accept weird people the way they are and interact with them anyway. And so voltage is just one of those things. We just got to accept that voltage is going to be weird. It's going to make us a little uncomfortable, and we're going to use it. Okay? So we're going to start by building it similar ways to how we've built everything else up to this point. Okay? Zach, stop. We need you here, man. You can finish your calculation later. Okay, so a review of example 1. If I'm not mistaken, this is the first example. No, we've seen this example before. I can't remember where, but we've definitely seen this example before. I want to find the electric field and the direction 75 centimeters east of a 2 microcoulomb charge. Okay? So the electric field at that point right there, caused by this guy here, electric field from a charge is given to us by E equals KQ over R squared. It's on the formula sheet. You forget it. There it is. So that's 9E9. The charge is 2 microcoulombs, E negative 6. The distance is 75 centimeters, so I convert that to meters, 0.75. We're going to square that. And I'll just tell you what that value is because you could calculate it on your own, or I could just give it to you in this case. For the sake of time, that's 32,000 newtons per coulomb. Now, B, C, and D all say, find the force on a blah charge placed at that point. So what we're going to do for B, C, and D is just an application of, I've got an electric field. If I put my charged object in that electric field, what's the force on it? So it's an application of this formula here, F equals QE. And what we're going to do is we're going to vary Q and see what happens. Okay, if I put a 1 coulomb charge at that point there, that's just my 1 coulomb charge times my electric field strength. 1 times 32,000 is 32,000. That was measured in coulombs. That's newtons per coulomb. My coulombs cancel, leaving me with newtons, which we should get because it's a force. A 1 millicoulomb charge is just going to be 0.001 times 32,000. You quick mental mathematicians are just going to say that's 32. And then the last one here says, well, we want to find the force on a 2 millicoulomb charge. So that's going to be 0.002 coulombs times 32,000. We can just take the result that we got for C and double it. 64. And so this is just some review. We had a connection here. We said, well, okay, F is equal to QE. It's also equal to, this is where we started, KQQ over R squared. And it was this guy right here that we said was equal to E. We took our variable force. And we say, okay, well, if I apply a force over a distance, that's just potential energy. Rather than rederive it, we got this guy here. Our potential energy was KQQ over R, the potential energy that exists between two charged particles. Now we're going to analyze some stuff. The electric field, if we look at what we've got here, electric field newtons per coulomb, tells us the newtons of force per coulomb of charge placed at that point. Okay, so if I put a 1 coulomb charge there, there's 32,000 newtons of force that act on it. If I put a 0.001 coulomb charge there, it's 32 newtons of force that act on it. If I put a 0.002 coulomb charge, it's 64 newtons of force that act on it. That's what the electric field does. It's a relationship. It gives us a relationship between force and charge at a point in space, given some properties of that point in space. Be cool? We can accept this? Okay. For energy, there is an analogous concept that tells us not the newtons of force per coulomb of charge, it's the joules of energy per coulomb of charge at that point. So I had this expression here before. I had my potential energy before, and I said, okay, at this particular point, if I put a 0.1, sorry, if I put a, let's say 1, if I put a 1 coulomb charge at that point, I could find the potential energy that exists between these two charges. Yes, that was the lesson we just did. Okay? But what if, instead of placing a charge at that point, I say, okay, this is a field point now. There's nothing actually there. What would the potential be? Or is there an expression that relates the potential energy from the charge that's given to this point in space? That analogous, am I kind of making sense? If there was something like that, well, then what would it be? So the joules of energy per coulomb of charge placed at a given point. Well, okay, let's look at that. Let's see what that is. I want potential energy per coulomb of charge. I'll call it Q. I had force per coulomb of charge was electric field. Potential energy per coulomb of charge is going to give us this expression here. PE is KQQ over R over Q. My Q's are going to cancel. And so I'm going to get this value here, or this expression rather. PE per coulomb of charge is just going to be KQ over R, the potential energy that exists at any point around a charged object. And it's this potential energy around a charged object, this field of possible potential energies, is what we call voltage. Okay? So V is what we get here, this potential energy per coulomb of charge equals KQ over R. So in gravitation, you had potential energy. Well, why did you had the potential to do stuff? Why? Well, because we lifted you above some massive object, and so you were likely going to fall. It was possible that at some point in the future, the energy you had stored up within you was going to be used. That makes sense for most people. What gets weird here is that voltage is not this energy is going to turn into this other useful energy. Voltage is you have the potential to do things later. We're layering the potentials now. You might possibly do things later, is the wording here. You could possibly do stuff later, should you choose to. Okay, so that is the idea here behind voltage. Okay, big V here stands for voltage. And the other name for this is where things get a little bit confusing, is sometimes we refer to voltage as potential. Okay? We say that the voltage is this, or that the potential of a space is this. Potential and potential energy, not the same thing. Potential is the possibility of potential energy later. Because you only get potential energy when you've got two charged things working together. I don't want two charged things. I want one charged thing. What is the possibility that around this charged thing there is potential energy later? That concept we call voltage because of the relationship between potential energy and this concept. We also call it potential. With a 9-volt battery, yeah. You could say that that is a 9 potential battery of having potential energy. It might have potential energy later. Okay, no, Nathan, see, you're doing exactly what I told you to do. Not to do. Just accept it, we're going to use it, and move on. Okay? Again, this concept is directly related to energy. You can see that right here. With energy, because energy was not a vector, we included the charges, the signs on the charges to give us some sense of whether work was going to be done or whether it was going to do work. Because potential energy is a scalar, voltage itself is also a scalar. So for the same reasons, we include positives and negatives on the charge when determining voltage. This lesson on page 382, we're going to connect all the dots. Flip the page, not to 382, but to 380. Okay, I am going to ignore this whole example 2. And in lieu of example 2, because I've done it all already, it was just the stuff that I did on the previous page, where I had P over Q, and then I actually said, well, P is KQQ over R, and then I divided that by Q, and I canceled some Q's, and I got V equals KQ over R. That's basically what they're getting at here. So instead of example 2, I'm going to direct your attention to this. We are now here. Voltage involves this guy here and this guy here. The two I have now just underlined in red. We've already used this guy here that I'm going to underline in green. We've used the potential energy. Actually, maybe I'll let, no, yeah, I'll leave them in green. We've now got our voltages. This one's coming. We're going to connect the change in voltage, the change in potential to a direct connection with electric field. It's going to be great. That's where things are going to get real messy. We're going to ignore that for the time being. We'll build up to it. So here we go. I've got, guys, stop talking, Ashton. I've got the same example because I want to get these things done so you guys can actually play with this stuff in class. Same example. A 2 microcoulomb charge, 75 centimeters from it, I've got a field point. We're going to find the voltage at that point there. Okay? Voltage is going to be connected to the potential energy that comes later. So, voltage at that point. The voltage outside a singular charged object is given to us by this formula here. I gave it to you on the previous page. We're going to use it here. Voltage, V, not velocity, big V, voltage, is equal to KQ over R. So that's going to be 9 times 10 to the 9. The charge that we're finding the voltage outside of is 2 times 10 to the negative 6. The distance is 75 centimeters, so in meters it's 0.75. Because voltage is a measurement of joules per coulomb, those are the units. The value you should get here is 24,000. And the units on voltage are joules per coulomb. Or sometimes we call this joules per coulomb. Volts. Voltage is measured in volts, also joules per coulomb. Kind of like how kilogram meters per second squared is just newtons. We looked at this and said, well, this is getting kind of cumbersome. We have one guy named joule and one guy named coulomb. Why don't we have one guy named voltage? Or volt. Last name was Volt, yeah. It's German, if I'm not mistaken. So, I want to find now, I found the voltage, the potential. Now I want to find the potential energy. If I placed a 1 coulomb charge there, I could find the potential energy using KQ over R. You did that in the stuff that you're working on now for homework. But now that we've got this concept of voltage, I could say, well, instead, PE, my potential energy, is equal to the charge I want to place at that point times the voltage available at that point, or the potential at that point. The potential to gain potential energy. Well, we're told that for part B, that's just 1 coulomb times 24,000 joules per coulomb is going to give us a potential energy of 24,000. And look what I've got here. V is just KQ over R. Multiplying KQ over R by Q, we could have just used this expression here, PE equals KQ over R. But by finding voltage, I have solved most of that problem for all possible charges I could place at that point. Now I'm just going to multiply this concept we call potential, or voltage, by whatever charge I want to place there, and I get the value for the potential energy of the system. That's the purpose of this concept. Zach, are you dying? And I would say that is the appropriate response. If at this point you're not a little bit uncomfortable, you've got two options. You're phenomenally good at physics, or you have so little clue of what's going on that you don't know that you should feel uncomfortable. Okay? Those are the two options. If you're comfortable with what's happening here, with not even a little bit queasy, you're really good. Or you're so lost you don't know how lost you are. This will change. That feeling will vanish because you're going to start using this and it'll get great. But the initial response to where we're going should be a little bit of unsettlement. So, same thing here. For part C, I want to find a 1 millicoulomb charge. Well, that's just 0.001, yeah. Times the 24,000. That's going to give us, that's joules, and that's going to give us 24 joules. And I don't need to do D. D is just going to be twice as big as that one. It's going to be 48 joules. Yep. Right. So, and the reason that we do that is because we get situations like that look like this. Okay, I've got two charged objects. Just hang in there with me, guys. I have two charged objects. We could find a whole bunch of things related to these two charged objects. But what we want to be able to do is say something like this. Well, I've got two charged objects hanging in space. I want to move another charged object from this above them to below them just by going like this. Without this concept of voltage, that gets really hard. Because now we would have to deal with potentials at different points and how potentials would change related to all these different points. But by using voltage, we have a quite nice way of dealing with this. This voltage, what I'm trying to show you with this example is that voltage allows us to scale up the problems that we're going to deal with really, really easily. So that's why we introduced this concept that would otherwise make us uncomfortable, because it makes everything that's common really nice. So here we go. Part A. Find the potential, i.e. the voltage, at point X. I want to review something with you here. Voltage is potential energy per coulomb of charge. How would I find the potential energy at that point there? If this is all I'm given, I want to find the potential energy at that point there, what would you do? I could find the potential, if I put a charge there, I'd find the potential energy from this guy here, the potential energy from this guy here, and I'd add them together, right? They're not vectors, I could just add them. Because voltage is built on that concept, it behaves the exact same way. I find the voltage due to that charge, the voltage due to that charge, and I combine them to find the total potential, i.e. the voltage, at that point. So let's do it. I'm going to color code these things. This guy here is going to be blue. So the blue voltage, V equals KQ over R. Should go up. So that's just going to be 9E9. That is 2.5 E negative 6. All over, we're told the distance between the blue guy and that point that we're dealing with there is 0.2 meters. So 0.2. We're working upwards for reasons that are going to become obvious in a second. That voltage, 99 times the charge divided by the distance, is 12,500 joules. Sorry. 112,500 joules per coulomb. And this guy here, that I am going to color code pink, is the same charge, the same distance away. The potential due to this guy is also 112,500 joules per coulomb. So the total voltage is just going to be the sum of those two. 112,500 plus 112,500 gives us a total voltage, V total, of 225,000 joules per coulomb, also called volts. That's the potential at point X. Sorry? The voltage is dependent on the distance. Yeah, no. Voltage is absolutely dependent on the distance. So that's part A. We're going to go through here and do B. Now we're going to work downwards because I got this charge down here. So now we're told we've got some point in space, y, 0.35 meters from this blue guy. What's the potential at that location? We use the same formula. So that's going to equal V equals 9E9. The charge hasn't changed. It's still 2.5 E negative 6 divided by this new distance, 0.35. That's going to give us a voltage V of 64,285.7 joules per coulomb. The pink one, because all the other values are the same, is going to be the same. V equals at Y 64,285.7 joules per coulomb. So V total at Y is going to equal the sum of those, which is 128,571.4. I have found my voltages at those 2 points. I'm going to skip C for a second. Because I want to show you where we're going here. So we're going to jump to D and it says, find the work. How much energy is it going to require to move a 1.25 millicoulomb charge from Y to X? So this tells us that I'm going to need work energy. This is part D. So initial energy plus whatever work I'm going to do, that's what we're looking for, is going to equal my energy in my final state. What kind of energy do I have at the beginning? I have potential energy. So I'm going to call this my potential energy at Y plus work is going to equal my potential energy at X. So my work is going to equal my potential energy at X minus my potential energy at Y. If we don't have voltage, there are now 4 terms here. Because I'd have to find the potential energy due to this guy and the potential energy due to this guy for that point, and the potential energy due to this guy and the potential energy due to this guy at that point, using my new charge object. But we've got voltage, so we can use a new expression here for potential energy. So work is just going to equal my charge Q times my voltage at X minus Q times my voltage at Y. Well, that Q is the charge that we're moving around. So I can just factor that out. I can say, well, this is just going to be Q times my voltage at X minus my voltage at Y, which is going to give me this expression here. Work is equal to Q. Vx minus Vy is just my final voltage minus my initial voltage. That's just delta V. So now I've got to change a new work formula. Work is equal to Q, my charge, times the change in voltage, which doesn't exist on the formula sheet. So we're going to add it. Work is going to be equal to Q delta V, which is only useful in specific circumstances, i.e. we're not dealing with kinetic energy here now. But that is a useful expression to have. So we can actually now go through and deal with this. Work is equal to the charge, the 1.25 times 10 to the negative 3 Coulomb charge that I'm moving between these two locations that have different voltages. Yeah, because it's a millicoulomb charge. 1.25 millicoulombs. My voltage at X we found was 225,000 minus my voltage at Y, 128,571.4. I will tell you the value of that is 120.5 joules. We have to do work to make that happen because this is positive. If it were negative, we'd be doing work to prevent that from happening. But because it's positive, we're actively doing that work. So you might be sitting there thinking, well, I had to do all these calculations anyway. How is this going to make things easier? Well, in the things that we're going to be working further in, you're going to be given the voltages. Like even like dealing with the plug at the wall. You know what the voltage at the wall is. It's 120 volts. Now you know. If you go to Europe, it's 240. So if I plug things in, Like there's different voltages, different potentials, possible potential energies provided by outlets in different spots. We're going to use, now that we have a relationship here between work done and voltage, we're going to start using, we're going to be given the voltage, and we're going to start plugging forward with that. So if you flip the page, we're going to sum up everything here. We're not going to actually do, there was an example there, I got rid of it. So if the charge begins and at rest, then the work is just going to be the change in potential energy times the charge, which is voltage times charge. Here we go. Sum up everything we've done. Divide this page into 4 quadrants. Straight down from the middle, and then straight across to that hole on the side. Top left, we've got electric force. Directly related to electric force was the electric field, which is going to go top right. They are related to and dependent upon each other. And then bottom left, we had electric potential energy. And directly related now to this idea of electric potential energy is what we're going to call electric potential, also called voltage. So electric force, we think back to where this all began. This started with the charge between this started with the force between two charged objects, given to us by this formula here. F equals kqq over r squared. This is a vector. So we use positive and negatives on the charge to give direction. So for this formula up here, we do not use positive, negative on Q, because we use them down here to give us that direction. So maybe that'll be easier to read. So the classic example of this would be if I had a positive charge here and a negative charge here, and I had another charge up here. How would I find the force on this guy here? Well, he would have a force to the up and to the right from this guy. He'd have a force straight down from this guy, and I would add the vectors to find the force on that guy there. From electric force, we moved to electric field. They said, okay, well, let's forget that I have two charged particles. I just want the one charged particle. What could happen if that thing was just hanging out there? So we got electric field, also a vector, given to us by this formula here, kq over r squared. Again, no positive and negative in the formula. We use positive, negative to give direction. So the similar analogy, the similar analogy to this guy here would be, what if I had this situation? A positive charge, a negative charge, and instead of another charge up here, I just have a point in space. Well, this guy would have an electric field that way, that guy would have an electric field that way. You would add vectors. And we have a lovely relationship that exists between electric force and electric field. That relationship is this guy here, F equals QE. was the formula that we had that bridged the gap between these two concepts. First two lessons. Now these last two lessons, electric potential energy and electric potential. We came up with this equation. PE equals KQQ over R. This is not a vector. Because it's not a vector, we haven't dealt with the positives and negatives that are associated with the charges. So in the formulation of this equation, we will use positives and negatives. And the lovely thing here with potential energy, they don't add like vectors because they're not vectors. PE total is just equal to the potential energy from 1 plus the potential energy 1 plus potential energy 2 plus ... plus potential energy n for every combination of particles that I have present. If I have a lot of particles and I want it to sum up a whole bunch of particles, calculus students, there's a connection here that's going to happen further down the road. It's a summation if you want to sum a lot of things real easy. You can integrate. It's coming later. N is the however n combinations of particles, however many there are ultimately. Okay, that was potential energy. Then we had electric potential, i.e. voltage. Voltage, we had this expression here, V equals KQ over R. Again, because there is a relationship between PE and V, voltage is also not a vector. So we use the positives and negatives to determine what the voltage is at a particular point in space. Similarly, V total is going to equal V1 plus V2 plus ... plus Vn. However many n is just however many there are. And again, just like the relationship between force and electric field, we have a relationship between electric potential energy and electric potential given to us by this equation here. I want to make sure I get it right. PE equals Q times V. And the next time I see you, whenever that will be, we're going to create a relationship between these two concepts. Not quite, because we're not going to create it. We're not going to go this way. We're just going to do this way. It's going to be great. To my knowledge, no. Well, kind of. Because work equals, well, there is. Because potential energy is equal to work, change in work. Sorry, work is equal to change in energy. Work equals a force times a distance, but the force is variable with distance, so we integrated it. The relationship between here is an integral. We're not doing that, because I kind of showed you once, and it's not relevant to what we're doing now. So there is a relationship between these two, but it involves more advanced mathematics that I'm not going to write down. That's it for this lesson. Welcome to voltage. Flip to 384. One, 2, 4, 5, 9, and 13. Sorry, what did you say about torque? Torque's coming back. Because we're going to see what happens when we put objects into electric fields, and we're going to see that electric fields cause objects to spin, and things that cause things to spin means that they're applying a torque to a thing. It's all coming back. It's going to be beautiful. We're getting to easily my favorite part of this course, because all the pieces just kind of click back together. And you realize we've been building a Lego castle this whole time and not just a whole bunch of little pieces. That's the end of the lesson.